chapter 14. Chapter 14 is on oxidation reduction reaction. We talked about it before. Oxidation is the loss of electrons. Reduction is the gaining electrons. If something's being oxidized, something else has to be reduced. Okay, they go hand in hand. Can't have one without the other. Okay. So let's see. Let's go through it. Chapter 14. We'll start on that. So an oxidizing agent takes electrons. A reducing agent loses electrons. In other words, an oxidizing agent causes oxidation. A reducing agent causes reduction. Oxidation numbers is a way of keeping track. They don't really mean anything. They're not valued. We're going to assign numbers to them, but they don't really mean anything. They just allow us to see what's being oxidized, what's being reduced, how electrons are moving. So let's take an equation from the book here. Let's take our sodium solid plus 2 H2Os goes to Na plus 2 OH minus plus H2 gas. Okay, now there's some rules of assigning oxidation numbers. Okay. The first rule, okay, these are listed right in your textbook, is any element that's all by itself is 0. So Na is going to be 0. H2 is going to be 0. Anything that's by itself is going to be 0. So we're going to assign sodium gets an oxidation number 0. Hydrogen gets an oxidation number 0 because they're the element. There's nothing else attached to them. They're just pure by the element. The oxidation number of fluorine is always going to be -1. So if you have fluorine, it's going to be -1. Oxygen is going to be -2. Okay, so let's assign oxygen here is -2, and oxygen here is -2. Okay, I'm just writing the numbers above each element. Okay, the halogens, the rest of the halogen, chlorine, bromine, and iodine are -1 also. So chlorine, bromine, iodine are -1, just like fluorine. These are the rules in order you have to use. So if oxygen is bonded to chlorine, oxygen takes precedence of the rule, and then chlorine. Okay. If hydrogen is bonded to a non-metal, it's +1. If hydrogen is bonded to a metal, it's -1. Okay. So when OH minus hydrogen bonded to a metal. Okay. So hydrogen bonded to a metal is always going to be -1. Hydrogen to a non-metal is +1. Okay. And hydrogen here is bonded to, let's see, hydrogen here is +1. It's bonded to a non-metal, and it's +1 here. And there's all the numbers. Okay. You've also got rules that say it has to equal the charge on the element. So if this was Na plus right here, it has to equal the charge on the compound. So with Na plus, this has to be +1. Okay. You've got to equal the charge. Look at H2O. H2O has a -2 from oxygen and 2 positive ones. That comes out to -2 plus 1 is 0. Charge on water is 0. The charge on OH minus, oxygen is -2, hydrogen is +1. That's a net charge of -1. Okay. Hydrogen is 0. Okay. So if we look at this, all these numbers tell us is sodium went from 0 on the left side to +1. Hydrogen stayed the same. No, hydrogen went from +1 to 0. And oxygen stayed the same. Oxygen went from -2 to -2. Didn't change. Right? So there's our changes. So sodium has increased. It went from 0 to +1. So sodium has been oxidized. Hydrogen went from +1 to 0. It decreased. It's been reduced. Okay. That's what these numbers tell us. Oxidation numbers tell us what's been oxidized, what's been reduced. Oxygen is an increase in oxidation numbers. Hydrogen is a decrease in oxidation numbers. So those are our rules. And we can determine what's being oxidized, what's being reduced. I guarantee you'll see that on your final exam. Now we have to you'll see that, you have to find numbers for oxidation numbers in a compound. So let's say we'll take an example from your book. Let's do an easy one first. SOCl2. SOCl2. Okay. Now we know oxygen, I'll look at our order of steps, is -2. We know chlorine is -1. So now we got to solve to make that equal to 0 for sulfur. Okay, so let's put sulfur as X, and we have -2, and then chlorine's -1 twice. So that's also -2, and it has to equal the charge on the compound, which is 0. SOCl2 does not have a charge on it. So solve that, X is equal to 4. So sulfur is +4. So sulfur is +4, oxygen is -2, and chlorine is -1. That's that compound. That's how you assign numbers. Let's do one with a charge on it. Let's take HSO4 minus. Okay, now we got a minus charge. We know hydrogen is +1. It's bonded to nonmetals. We know oxygen is -2. We got to solve for sulfur. So we got +1. Let's do it a little bit backwards. Let's take X. X is our sulfur. And we know +1 for hydrogen, right? Then oxygen is -2, and there's 4 of them. So that's -8. And it has to equal -1. That's the charge on the compound. Does that make sense? I'll stop for a second and see if. Is that making sense how to set that up so far?
Yeah, I was wondering, because I was gonna ask in the beginning, but you're going so fast. You said oxidation is when an electron loses something, and then you said reduction is when.
Right. Oxidation is when you lose electrons, loss of electrons. Now remember, electrons are negative. So when you lose a negative charge, it becomes more positive. So when we're comparing oxidation numbers, when the number increases because you've lost a negative charge, that's oxidation. When the number decreases, that's reduction. So oxidation is the loss of electrons, reduction is the gaining of electrons.
Okay, I just wanted to make sure.
Right, you're right, because it's hard to conceptualize because electrons are negative. So if you lose electrons, okay, the number becomes greater because you're losing negative charges, it becomes more positive. Okay, if you're gaining electron, you're gaining negative charges, so the number becomes smaller. Okay, so we solve for this, X equals, we add 8 to that side, that becomes 7. And then where are we at? X. Oh, we add 8. 8 minus 1 is 7. 7 minus 1 is 6. Okay. So in sulfur equals +6 in this case. Sulfur was +4 here. Sulfur is +6 here because it has to equal the charge on the compound. Because 6 plus 1 is 7. Minus 8 is -1, which is the charge on our compound. Let's do a couple more just to make sure you got it. So let's do SO3 sulfate ion. SO3 2 minus. Okay. We know the charge on oxygen is -2. Okay, the sulfur will have to put its X, so I have to solve for it. So X, and there's 3 of them, so it's -6 equals -2, which is the charge on the compound. So X equals 4. So of sulfur is +4 in that one. Okay. So now we can assign oxidation numbers to almost anything here. So let's find out, let's take a reaction. Let's take one from your book again. Let's say, oh, let's do the long one here. I'll explain everything forward. Let's do 8H plus MnO4 minus plus 5 Fe2 pluses goes to 5 Fe3 plus Mn2 plus manganese 2 plus 4 H2Os. There's your equation. So you're going to see something like that on your final, and it will say choose the correct answer. It'll say hydrogen is oxidized, hydrogen is reduced. Manganese is oxidized, manganese is reduced. Oxygen is oxidized, oxygen is reduced. Iron is oxidized, iron is reduced. Pick the ones that are true. So you have to assign oxidation numbers to everything. Okay? So let's put oxidation numbers as, we'll put down here, hydrogen is +1. Because it's hydrogen is a positive charge. It has to equal the charge on the compound. So hydrogen is +1 here. Oxygen, you know, is -2. Okay, so we have to solve manganese. And then oxygen is -2 4 times. That's -8 equals -1. So X equals 7. So manganese is +7. Oops, I should have put it down the bottom. Well, come back here, guys. Because we just ran out of, it's not going to erase. Manganese is +7. And iron is +2. Right? So now we have everything on the left side assigned an oxidation number. And iron on the right side is going to be +3. Because that's a charge on it. Manganese is going to be +2. Hydrogen is going to be +1. Oxygen is going to be -2. So there's your oxidation numbers. Just find the rules that we set down. So now make a list. This is the easiest way to do it. Hydrogen. Hydrogen went from +1 to +1. Okay. Manganese went from +7 to +2. Oxygen went from -2 to -2. Iron went from +2 to +3. Oh, come on. Okay. Those are all the elements in your chemical equation. So what's been oxidized, what's been reduced? Hydrogen stayed the same. Oxygen stayed the same. Okay. Manganese went from a +7 to a +2. So it's been reduced. It's gained negative charges, made the number lower. So manganese has been reduced. Iron went from +2 to +3. It got bigger in number. So it's been oxidized. So those are the two you would circle on your final. You would say iron has been oxidized and manganese has been reduced. Does that make sense?
Yeah.
All right, perfect. And section 2 on chapter 14. We'll go through that. Let it pull up here on the computer. There we go. And there's types of oxidation reactions. We can have combustion reactions. We have single place reactions we've done before. Let's do a combustion reaction. Okay, combustion, and let's do propane. Let's do butane. Okay, butane is C4H10 plus oxygen goes to CO2 plus water. Okay, so balance it. 4 carbons, 10 hydrogens, and how many oxygens do we need? 8, and finally we need 13. So we put 13, it actually be 13 over 2. So it'd be 13 and then halves, and this would be 8, and this would be 10. Kind of messy there. There we go. Okay, now we're balanced, right? 8, 8, 20, 20, and 26, and 16, and 10, 26. All right. What's been oxidized? What's been reduced in a combustion reaction? Let's assign our values. Okay. So hydrogen's +1. Carbon in this case is, now you got to figure it out. You got 4 carbons, so 4x plus 1 and 10 times, so plus 10 has to equal 0, which is the charge on the compound. Okay. I mean, the magnitude of these numbers don't matter. It's just we have to compare and see what happens to it. So 4x equals 10, x equals 10 over 4, which is 2. Dang it, why does this keep doing this? So 10 over 4, which is 2.5. 2.5. So 2.5. So carbon equals 2.5 positive. Oh, negative, I'm sorry. Negative 2.5. Yeah, because 4x equals negative 10, x equals negative 2.5.
Sorry, I'm gonna meet Jeannie at the office to get the list of inventory so we can do inventory tonight.
Okay.
Until the lady tomorrow.
Oh, no problem. All right, so x equals negative 2.5. So that's what carbon equals to. Oxygen is equal to? What's oxygen equal to? This is the element. It's O2, nothing else combined to it. So in this case, oxygen equals 0. This is just the element of oxygen. Okay. Again, CO2, oxygen equals negative. Oxygen equals negative. Why does this thing keep moving on me? Oxygen equals negative 2. And carbon equals, carbon is X. And then oxygen is negative 2. 2 times that's minus 4 equals 0. So X equals positive 4. Okay. So in this case, it's plus 4. And then hydrogen is +1. Oxygen is negative 2. We got all our values now. Okay. Compare them. Let's do carbon, hydrogen, and oxygen. Those are our 3 elements. Carbon went from negative 2.5 to +4. Hydrogen went from +1 to +1. Oxygen went from 0 to negative 2 on both sides. Okay. So carbon went from negative 2 to 4. What's happened to carbon? Oxidized or reduced? Let me pull the chat window up here too. That's what I forgot to do. Okay, I got the chat window up here too. So if you want to enter in chat, you can also. I should be able to see it.
Did it become oxidized?
Okay. Yeah, because it must have been greater. Perfect. Carbon has been oxidized. Hydrogen, no change. Oxygen has been reduced, has gotten smaller. That's our combustion reactions. Combustion reactions are oxidation reduction reactions. So now you know how to, all oxidation numbers are so we can use them to compare. They don't mean anything. Like the value of carbon negative 2.5 doesn't mean anything. We're just using it to compare what is on the other side. That we can tell if something's been oxidized or reduced. Okay. And then we did equations. You have what's called we use half reactions for it, and we can do the single substitution reactions. And we have what's called an activity series, and that tells us what is going to replace what. Okay, so if we take, I don't think I have the activity series on here, do I? Let me see. No. Okay. The activity series in your book, it lists in section 14.2. It just lists the different elements and how reactive they are and what will replace what. In other words, if we were going to react, say we had the action of iron, solid. So we dip an iron metal into a nickel solution, Ni+. it would form Fe2 plus nickel solid. It would plate it like electroplating. You put nickel solid. If we took iron 2 plus and put it with nickel solid, we would get no reaction. Okay? It has to be lower in the activity series. If you look at the activity series, you look for Fe. Fe is iron. You find iron is roughly about halfway through. Okay? That's your activity series. And you look for nickel. Nickel is below iron. Okay? So iron is more reactive than nickel. So if you react iron, it's not going to replace the nickel. Okay? If you look at activity series iron here, iron is above nickel on the activity series. So it will react. Okay? So we react with Ni2 plus and form a reaction. But if it's higher up, like iron on this one here, the iron, ion, if the ion, okay, is higher up, that you can see the iron, and you see nickel below it. If the ion's higher up, it's not going to react. Okay, another way of saying that is that the metal, the solid, if the solid is lower than the ion, there's no reaction when you look at activity series. So if we look at aluminum, let's say we have aluminum solid plus, let's put in calcium. Would there be a reaction? Okay. You look at aluminum, aluminum is up high. Okay. And the calcium ion is above aluminum. Okay. So if the ion is higher, okay, just like iron was above nickel, just gonna double check my chart here. Iron, so okay, so you look at your solid, your aluminum, and then find the calcium. Calcium's above it, so calcium more active. So you would form Al3 plus calcium solid. If we took gold and put it with zinc, okay, gold is at the very bottom. So gold doesn't react with anything, just like gold doesn't react with acids or anything else. You get no reaction, okay? Because the solid is lower down the activity series. Okay? If the solid is lower than the ion, you get no reaction. The solid has to be above the ion, so there's a reaction. That's your activity series, and that's how it works. And like I said, you'll get that for the test. Just remember where that is so you can look it up. I don't want you to memorize all that. Just you look it up. If the solid is below the ion, there's no reaction. If the solid metal is above the ion, it's more reactive, you're going to get a reaction. That's an activity series. And you can predict what's going to react to what with what. Okay. So let's look at you have a list right here. Let's do 4 little things right here. So let's see if you understand it. Okay. This is based on the activity series, which elements were reduced to elemental iron. So say we have Fe, Fe2 plus. Yeah, which can reduce iron to elemental iron. Plus some compound X goes to Fe solid plus X plus, say 2 plus, whatever it is. Okay, so if we put in for X, we put in calcium. Okay, we look at activity series, we see calcium is above, let's see, let me double check. Okay, calcium is above iron. Okay, so calcium is above iron, you'll get a reaction. Okay, you'll have Fe, iron Fe2 plus, okay? So calcium will react to form Ca2 plus and iron solid. How about magnesium? Look at magnesium. it's also magnesium is, okay, magnesium is above iron. So you get a reaction. Fe solid plus Mg2 plus. And let's look at chromium. Chromium is also, chromium is above iron. So you get a reaction. You'll get chromium solid plus Cr2 plus. I'm not chromium solid, I'm sorry, F iron solid. Okay, and let's do silver. Now silver is below iron. If it's below it, it's not reactive and you'll get no reaction. So when you react it with calcium, magnesium, or chromium, those are all above iron, so you get a reaction. Silver is below iron, you'll get no reaction. Okay? That's how you use your activity series. Let's balance, we got balanced equations. We did net ionic equations already, we got that. All right, using activity series, which you just used. Okay. Just indicate whether the metals react with an acid. Remember, acid is H+. So look at hydrogen on your table. Okay, we have gold. We have nickel. We have platinum. And we have chromium, Cr. Okay. We want to know if those react with hydrogen. So we look at we go back to our activity series, and we find hydrogen. There it is. Okay, now we look at hydrogen and we say gold is below hydrogen, so no reaction. Nickel is above hydrogen, so we get a reaction. Okay, it goes to Ni2+. So gold, acid will dissolve nickel. Platinum is below hydrogen, so it will not react with an acid. Chromium is above. So chromium is above, go to Cr2+. Okay. So if it's below if the metal is below what you're reacting with, you'll get no reaction. So that's why gold can hold acid. Platinum will not be dissolved by acid, whereas nickel or chromium will be dissolved by acid because of the activity series. So you what's more reactive. Okay, perfect. Let's go to the next one here. Okay, we're gonna do half reactions so we can add them up and react the two different compounds together. So if we have an oxidation of zinc, let's say we have zinc solid goes to zinc 2+ plus 2 electrons. Remember, you have to, the left side and the right side have to have the same charge. So the left side has 0, so the right side has to have +2 and -2. That's where the 2 electrons come from, 2 negative charges. The other reaction is copper 2+ goes to copper solid. And this is 2 electrons here. Okay. So the top one is oxidation. You're losing electrons. The bottom one is reduction. You can add those equations together to get the total overall reaction, oxidation, reduction, reaction. So you would have, what you have to do when you're going to do this is these are going to be spectator ions. So those have to be the same. If the top one was 1, you'd have to multiply the whole thing by 2. A number of electrons has to be the same. Okay? If something's accepting electrons, something's giving them off, it's got to be the same number. Okay, you can't just have electrons floating around in space. So if something's giving off 2 electrons, something else has to accept 2 electrons. Okay, so you got to make sure those numbers are the same. Multiply your equations, make sure they're the same. We'll do some examples to show you in a second. But what you would get 2 electrons plus Cu2 plus zinc solid goes to zinc 2 plus copper solid plus 2 electrons. 2 electrons cancel, and you're left with your oxidation reduction reaction. Copper 2 plus zinc goes to zinc 2 plus copper solid. Okay, now let's say we're in a reaction of, let's say, sodium. Let's go sodium solid goes to Na plus 1 electron. Okay, charges are balanced. And let's say we go to, let's use copper again. Let's say we have 2 electrons plus copper 2 plus goes to copper solid. Now those are your 2 reactions. The top one's oxidation, bottom one's reduction. Okay, I lose electrons or gain electrons. Now, look at the difference. You can see there's 2 electrons here, there's 1 electron here. Remember what I said, the number of electrons has to be the same so they can cancel on both sides. You can't just have electrons flying off into space. If something's giving off, something has to accept. So you got to make sure they're the same number. So how to make sure they're the same number? We multiply the top equation by 2. We have 2 sodiums, 2 electrons. Now we can add the equations together because the electrons are the same. This number has to be the same on both sides. Okay? So our equation becomes 2 Na solids plus copper 2 plus goes to 2 Na plus copper solid. And that's our oxidation reduction equation. And we got it by adding the 2 half reactions, the oxidation and the reduction. When you do that, you just have to make sure the electron value is equal. Because you gotta, if you're losing 3 electrons, you gotta gain 3 electrons. Okay, they've got to be accounted for. They can't just go flying up wherever you want them to. All right. So let's balance that. Let's do an example. Let's go and write the half reactions for each one. So let's say we have, let's do the same thing. Let's do it backwards now. I want to write the half reaction for calcium solid plus chlorine. Okay, it goes to calcium 2 plus 2 Cl minus. Okay, so there's our 2 reactions. And there's our 1 reaction. Okay, now we're going to break it into 2 half reactions. And this is calcium solid. So we have calcium, that was our solid, goes to calcium 2 plus. Okay, where do the electrons go? The right side or the left side? Electrons have to go on the right side because it's a positive charge. And there's a +2, so you have 2 electrons. That balances your charges. So now the left side has 0 charge, right side has 0 charge. Let's do chlorine. Cl2. Okay. Cl2 goes to 2 Cl minus. Electrons have to go on the left side. Okay, so your charge is balanced. Okay, calcium is being oxidized because it's losing electrons. Chlorine is being reduced because it is gaining electrons. You're adding electrons to it. There's your 2 half reactions. Okay. That's how batteries work, reduction, oxidation. That's how we do plating. Okay. That's what I'm covering in that section. Dun, dun, dun. And then we've got chapter next 14, balancing reduction oxidation equations. All right. So in balancing them, you have to not only balance the mass like we did before, but you have to balance the charge. So let's take an example of reduction oxidation equation. So remember, the charge has to be equal and the number of elements almost have to be equal. So let's take calcium solid plus chromium 3 plus goes to calcium 2 plus Cr solid. Now, the balance, one calcium, one chromium, but it's not balanced. Okay, because on the left side is a +3 charge, on the right side is a +2 charge. Okay, it has to be equal. So in oxidation reduction equations, not only do you have to balance the elements, you have to also balance the charge. Okay, so we can balance the charge by putting a 3 and 2 common denominator is 6. So I can make this have a +6. I put the 2 here. And I can make this have a +6 by putting a 3 here. And then I got to balance my element, 3 calciums, 2 chromiums, 2 chromiums. Okay. Now, I'm balanced, my elements are balanced, 2 chromiums, 3 calcium, and my charges are balanced. I have +6 on the left, 2 times +3, and I have +6 on the right, 3 times +2. And I'm balanced. So you have to remember to balance the charge also when you're dealing with oxidation reduction reactions. Okay. And you can do that with the half reactions also. In other words, if we had calcium, let's go back and just go back to our equation and say calcium plus Cr3 plus goes to calcium 2 plus chromium. Okay, that's what we originally started with. And we just did it on by side. But what we can do is we can take calcium, break it into half reactions like we just did. Calcium goes to calcium 2 plus. Okay, and then this is going to require 2 electrons. There's our oxidation half, because that we are reducing number of we're losing electrons. Chromium goes from chromium 3 plus to chromium solid. This we have to gain. We have to add 3 electrons. Okay. Remember I told you, you have to make them the same number. So we have to make the lowest common denominator between 3 and 2 is 6. So I got to multiply this side by 3 and to multiply this equation by 2. So I end up with 3 calciums goes to 3 Ca2 pluses plus 6 electrons. The bottom up by 2, I got 6 electrons. 3 times 2 is 6, plus 2 chromium 3 plus goes to 2 Cr solid. Add that together. I'm going to come up with the same answer we got last time. Okay, we're going to come up because the electrons cancel. Once you made them the same, you got 3 calciums plus 2 Cr3 plus goes to 2 Crs plus 3 Ca2 plus. This is the exact same thing we have on top. Now I know it was easy to see this one, but sometimes you get more complicated and it's not easy to see. That way you can break them into half reactions and be able to balance your equation relatively easily. Okay, but just remember they have to be the same charge also. Let's do another one, make sure you understand it here. Barium reacts with cobalt nitrate. I want to find one that you can balance a little bit harder than that. No, that's not what I wanted to do. Let's do, okay. Elemental barium reacts with, let's do one way from the book. Barium reacts with solution of cobalt 2 nitrite to produce barium chloride and elemental cobalt. Write your half reactions showing you can balance this. All right. So that's what we did. Let's write down in chemistry terms. So elemental barium is Ba, solid. Reacts with a solution of cobalt 2 nitrite. Nitrite is NO2. Okay. And it says it produces barium chloride and elemental cobalt. Okay. And this is barium 2. This is whoa, it doesn't make sense. It's written wrong in the book. Let's say elemental barium reacts with the solution of cobalt 2 chloride. That will make a whole lot more sense. It's a typo in the book. So barium, solid, elemental barium, reacts with cobalt 2 chloride. Okay, and it's going to go to barium chloride plus elemental cobalt. There we go. Much better. That makes more sense. So there's your molecular formula. Now let's break it into oxidation reduction. Oxidation is barium solid. Okay, is going to go to barium 2 plus. Because that's a salt, it dissolves. Okay, and we have cobalt 2 plus reacts with chlorine going to cobalt solid. Okay, so the top one barium, we have to add the electrons to make that equal to 0. We have to add the electrons over here to make that equal to 0. So barium is being oxidized, cobalt is being reduced. It's gaining electrons. And that's how you use half reactions. And you always make sure that these electron numbers are the exact same. That way you can always balance your equation. Because in oxidation reduction, remember you have to balance the charges along with the mass. Okay. And this is basic examples of electroplating, like when you have a chrome bumper on a car. That's how we do. We put down the metal, and then we react with a half reaction with the oxidation reduction, and then we plate. We cause the cobalt or the chrome, let's say the chromium ion, to chrome the metal, and that way you can chrome something. Silver plating or gold plating. When you get jewelry and it's gold plated, we do a half reaction with gold. That allows the gold to go from the solution of Au2 plus into the solid form, and it plates along the jewelry you're looking at. So this is how we do gold plating, silver plating, anything like that. This is your electroplating. And we're not going to do gold plating labs for experiments. Okay, but that's oxidation reduction reactions. Hydrogen-powered cars are oxidation with water. That's what hydrogen-powered. That's what hydrogen-powered cars like BMW produce one. Runs on water. Water breaks down into hydrogen and oxygen. We take the hydrogen, oxidation reduction reaction, causes power with hydrogen, and that's what runs the car. All right, so that is end of 14. Let's do chapter 15. So we can do that, and then we'll answer some questions. Then all we got left is chapter 16 on Wednesday, on radiation. All right, organic chemistry. We did one chapter on organic chemistry. I could talk forever on organic chemistry, but we'll reduce it real quick here. Basically, the world runs on a carbon cycle. Okay, we depend upon plants, plants depend upon us. Okay, plants take sunlight, they take energy. Okay, so energy from the sun, solar power, okay, reacted with carbon dioxide and water to produce glucose, C6H12O6, which is your sugar. plus oxygen. That's what plants do. Okay, that's photosynthesis. You get that in biology. So plants produce oxygen. We, on the other hand, do cell respiration. We take this glucose, C6H12O6, and we burn it in our bodies. We combust it by reacting with oxygen that we breathe in to produce carbon dioxide and water, which is the starting point for photosynthesis. And photosynthesis feeds into us. So it's called the carbon cycle. Plants and trees take in carbon dioxide and hydrogen with the energy from the sun and produce sugar and oxygen. We take that sugar that's produced, burn in the presence of oxygen in our body from metabolism, and produce CO2 and water in the process. Okay? That's the carbon cycle. And this gives off energy. Because when we burn energy, we produce heat, we sweat. Whenever we make energy, we produce energy. Plants take that energy in to make that for us. Okay. And we're going to talk about covalent bonds. We're going to talk about Lewis structures again. Lewis structures are very special things with carbon. Remember, we have the octet rule. Carbon has 4 valence electrons. We learned that before. 4 valence electrons. So carbon can have 4 bonds to it. It can either be carbon, can bond to hydrogen, 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 hydrogen. Okay. Or carbon can have a double bond. Carbon double bond can bond to hydrogen, 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 hydrogen. Okay. Or carbon can have a triple bond. But every one of these cases, carbon has 4 bonds. If you look at any of the carbon there, it always has 4 bonds. It can be single bonds, it can be double bonds, it can be triple bonds. Okay. It has 8 valence electrons. Hydrogen has 1 valence electron. Okay. So it has a duet rule. It has 2 to fill its shell. Okay. Carbon has 4, so it wants 4 bonds. Nitrogen has 5. It wants 3 bonds. Remember, nitrogen has 5 valence electrons. Remember how to determine valence electrons. Look at the periodic table. Carbon is 4. Okay, look at group 1A, sodium is 1. Magnesium group is +2. Aluminum group has 3 electrons. Carbon has 4. Nitrogen has 5. Oxygen has 6. Fluorine has 7. And then the noble gases all have 8, and they're stable. Now, so you determine the number of valence electrons. So nitrogen has 5, so it wants 3 bonds. Okay. Oxygen has 6, so it wants 2 bonds to fill where those gaps are. Fluorine has 7, it wants 1 bond. So it'll share 1 electron. So carbon's going to have 4 bonds, nitrogen wants 3 bonds, oxygen wants 2 bonds, and then the fluorine, chlorine, bromine ion, they want 1 bond. Okay. That's all because of the valence electrons, which we talked about. Okay. Let's go to, remember we talked about isomers. Isomer has the same chemical formula, different chemical shape. Let's take a look. Let's look at a very simple one. Okay. Every carbon has 4 bonds, fluorine has 1, and hydrogen has 1, which they want. Okay. If we put the, actually, let's do it this, I made a mistake. Let's put fluorine right here again. There we go. That's 2 carbons, 2 fluorines, 2 hydrogens. An isomer of that would be the same chemical formula, C2, H2, F2, but a different chemical arrangement. Okay. Now the 2 fluorines are on the same carbon atom. They will have different physical properties when that happens. So those are isomers. Same chemical formula, different chemical structure. Okay. And you get some really long different isomers with the long chain hydrocarbons that we're dealing with. So that's what's called an isomer. Same chemical formula, different chemical structure. Different physical properties. Okay, the more carbon atoms you have, the more isomers you can form. Okay? Even we don't have any attachments to it. Let's say we had let's say C5 H12. Okay, you have 5 carbons, and we have 12 bonded hydrogen. Every one of those lines is a hydrogen. 3, 5, 7, 9, 10, 12. Okay, there's a hydrogen in every one. That's one isomer. We could also do this. We could do, okay, carbon like that. And give every carbon 4, every hydrogen 1. That's also C5H12. Or we could do this. Okay, and then do our hydrogens. Okay, that's also C5H12. Again, different isomers, and the more carbons you put, the more there are. You can go up to hundreds of different types of isomers. Okay, but you have to just realize an isomer is the same chemical formula, same number of carbons, same number of hydrogens, but a different chemical structure, different shape. The different shapes will have different physical properties, different melting points, different boiling points, etc. Okay, so those are isomers. Okay, so we talked about the Lewis structures, and there's different ways of representing these structures. You could put C5H12, you could draw it like this, or you could say CH3, CH2, 1, 2, 3 times, and then CH3. That's your condensed formula. Because this is a CH3 right here. And there's 3 CH2 groups right here. And there's another CH3 group right here. Now, the most common way to represent it was called a line structure. We're not getting into too much of these, but this is how you see it in a pharmacy and in your different medicine stuff. You'll see different line shapes and different circles. So C5, you could draw as 1, 2, 3, 4, 5. That's exactly what we do. The end of every line is a carbon, and at the bend. So there's a carbon here, there's a carbon here, there's a carbon here, there's a carbon here, and there's a carbon here. That's 5 carbons. Okay. And if there's nothing else there, there has to be hydrogens. So at carbon number 1, there has to be 3 hydrogens because you have to have 4 bonds. At carbon number 2, there's only 2 hydrogens because again, you can only have 4 bonds. At carbon number 3, there's 2 hydrogens to give it 4 bonds. At carbon number 4, there's 2 hydrogens to give it 4 bonds. And at carbon number 5, there's 3 hydrogens to give it 4 bonds. Okay? So you can have the condensed formula, or you can have the line formula. The line formula is most commonly used in pharmacology and nursing, things like that. All right. So let's do a couple just to give you an idea how to do it. Let's do the Lewis structure. All right, say the Lewis structure is, and I'll draw the hydrogens this time so it doesn't get too confusing for you. Okay, there's our CH3, CH2, that's a hydrogen, and C, let's put 3 fluorines here. Okay, that's a structure for you, Lewis structure. Okay, you have actually dots around the fluorine because there's 6 around each one of these because fluorine has 8. Okay, now you can also draw the condensed form we talked about, which the first carbon is CH3. Okay, carbon with 3 hydrogen bonds. Then you have a carbon with 2 hydrogens, CH2. Then you have a carbon with 3 fluorines, CF3. That's your condensed formula. just tells you what you have. Your line formula is carbons and hydrogens. So there's 3 carbons. So 1, 2, 3. And at the end, at the third one, there's 3 fluorines attached. Okay. So there's your carbon number 1, at carbon number 2, and at carbon number 3. At carbon number 1, there's 3 hydrogens to make it 4. At carbon number 2, there's 2 hydrogens. And at carbon number 3, there's 3 fluorine groups to give a 4 bond. All right. Let's do one more. And then the big skeletal structures, we'll go over that for pharmacy. You have different resources, but let's do, let's make one up. Let's do, an OH group, a hydrogen, carbon, fluorine, hydrogen, CH2, CHC. Let's do a dialcohol. Okay, let's do that thing. Okay, condensed formula. You write the first carbon is CH3, right? The second carbon is C. And I'll put a little parentheses there to just make sure it's separated, OH and H. We have an OH group and H, just to keep the H's separate, put little parentheses. The next carbon is carbon with a chlorine and a hydrogen. The next one is CH2. The next one is CH3. That's how you write the structural formula. Again, the parentheses are just here to help show you that it goes with the carbon that comes before it. When you have what's called, oh, wait, I forgot. Hold on. CH2OH. I made a mistake. There's an OH group right there. There's 2 hydrogen and then an O and an H group. So now let's draw the line formula. How many carbons total? 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5 carbons. At carbon number 1, it's CH3, so we leave it. At carbon number 2, there's 1 hydrogen, so we don't put that on there, but there's an OH group. So carbon number 2, we draw an OH group. At carbon number 3, there's a chlorine group. And then a hydrogen, carbon number 4, CH2. And then here, there's an OH also. So we just don't include the hydrogens because they're assumed. So here we've got carbon number 1, 2, 3, 4, and 5. So at carbon 1, we have 3 hydrogens. At carbon number 2, we have 1 OH group and 1 hydrogen. At carbon number 3, we have 1 chlorine and 1 hydrogen. At carbon number 4, we have 2 hydrogens. Carbon number 5, we have 1 OH group and 2 hydrogens. And those are the different types of forms you're going to see. Again, it's just a very basic introduction. Okay, the next group on chapter 15 is functional groups. Okay, functional groups are ways of identifying what's attached to a molecule, what's attached to a compound. This is a functional group right here, OH. That's what's called an alcohol. This is a chlorine. It's called a halogen group. And then OH is an alcohol. Those are the different functional groups. We'll go over the different functional groups in a second here too. But if you have all single bonds, that's an alkane. Alkane is carbon with all single bonds. Alkene, that's an A and E. Alkene is an E and E. Those are double bonds. Those are single bonds. That's a carbon compound with at least 1 double bond in it. And then you have alkynes, which is a triple bond. So if you see the word alkane, you know it's all single bonds. If you see it's an alkene, that means you can have at least one double bond. Or if you see the word alkyne, you have at least 1 triple bond. So A and E is single bonds, E and E is a double bond, Y and E means it's a triple bond. Okay? And you can also have what's called cyclical structures. So cycloalkanes. You can have, this is mean they're in a circle, they're connected. Okay, so let's take propane. Propane is that, which is carbon, CH2, CH3. Okay, that's propane. Propane, like for gas fuel. This is propane. This is propane. Same thing. This is cyclopropane, which means they're connected because there's 1, 2, 3 carbons, and they're in a circle. Well, but it's connected. That doesn't mean it's a little circle. It just means it's a cyclical structure. It doesn't have an end. Okay, there's no end point or beginning point. So that's cyclopropane. You could have cyclobutane. Butane is 4 carbons. Okay, you can have cyclohexane. Hexane is 6 carbons. Okay, every corner or every bend is a carbon. 1, 2, 3, 4, 5, 6. Those are your line structures. You can be straight lines or they can be cyclical. Okay, and we'll learn what the names are. You have a chart in your book, like, hey, you do not have to memorize this. If there's 1 carbon, it's methane. Meth means 1 carbon. 2 carbons is ethane. 3 carbons is propane. 4 carbons is butane. 5 carbons is pentane. 6 carbons is hexane. 7 carbons is heptane. 8 carbons is octane. 9 carbons is nonane. And 10 carbons is decane. Oh, excuse me.
Bless
All right.
you.
So those are the 10 what you need to know. Thank you. Okay, so there's a chart. It's table 15.2. It's right in your book. Just have to know what they mean. Don't memorize them. You can always look at your book on the exam. So if I had 4 carbons, you can look it up and say C4H10. That's butane. So you're sure the first part, but, you know it's 4 carbons. Again, methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. That's 1 through 10. Okay, we won't go any farther than that. Okay, you got cyclopropane, cyclobutane is in a circle. What else? Draw the structure. Let's see where we're at. Okay. If you wanted to draw, if I asked you what this structure was, what would you say? You saw that on your final exam. What do you say the name of that is? How many carbons? 1, 2, 3, 4, 5, 6, 7, 8 carbons. It's all single bonds, right? Everything's a single bond that's connected to it. That's an 8. That allows you looking at 8. Okay, that is octane. 8 carbons, all single bonds. That's octane. We did alkenes and alkynes. And we did that. There is one special compound you should know about. It's a lot, because it's almost found in all medicines that we use. It's called a benzene ring. Benzene ring is a cyclohexane with alternating double bonds. So every carbon has a hydrogen on it, just one hydrogen. That gives it 4 structures. And that's a very stable compound. This is benzene. Benzene is found in most medications with a nitrogen group usually. Benzene rings, what's called, they're very biologically active. We see them in a lot of medicines. Benzene was used as a cleaning compound in a lot of solvents in the 1960s. And then they realized that a lot of janitors were dying of liver cancer. They determined and they found out that the benzene that they were using as a cleaning, it's a great cleaning product. Okay, it's carcinogenic. It causes liver cancer. So we use benzene as a great solvent. We use it in the lab. If you use it in the lab, you use it in the hood and use it very carefully because it's extremely carcinogenic. Okay, if you work at a hospital, a clinic, you use what's called phenols to clean, disinfect surfaces, right? Phenols are a benzene ring, but they have an OH group on top. Those are not carcinogenic, and they make a great cleaning compound. Okay, you can have toluene. Toluene is a great solvent. It's a benzene ring with a CH3 group on top. Okay. Now, if you take toluene and you add 3 nitro groups to it, we put nitrogen groups on that, we have trinitro toluene, which is TNT. That's dynamite. That's nitroglycerin. Explodes very rapidly. Okay. Benzene rings are very reactive, very biologically reactive, very reactive to a lot of compounds. So benzene rings are very common in dealing with chemistry. You'll see those in a lot of things. Okay, different functional groups we talked about. When we have functional groups, a lot of times you'll see an R. R just means a carbon chain. Just means it's a bunch of carbons, 2, 3, 4, 5, 100, doesn't matter. R just means a bunch of carbon chains. When R is bound to an OH group, that is an alcohol. Okay, so we have any carbons bonded with OH, when the OH is taken up, that is an alcohol. Okay, when instead of an H group, if that H was replaced with another R group, so instead of H, you put another carbon on that, that's an ether. Those are ethers. Those are very volatile compounds. Okay? That's when there's an alcohol between them. Now, if you look at, we do a lot of condensation reactions in chemistry. If you have, let's say we have CH3, CH2, OH. That's ethanol. That's vodka, basically. And say we react it with, let's put another CH3. Let's just write it backwards here. CH2, CH3. Okay. If we add these together, water is a very stable compound. So we can take an OH from here and an H from here. And that would give you CH3, CH2O, CH2, CH3. That would give you an ether. That's how we make an ether, which what's called a dehydration reaction. We take water, we take that plus that gives you this plus water. Because we took an H from one end and an OH from the other end to give you water. Okay, that forms an ether. So now you have an alcohol, and an ether. Those are 2 functional groups. And there's more, don't worry. Okay, and those are condensation reactions. We can make all kinds of things. We're just removing an H and an OH from an alcohol group. Okay, that's where we go a lot of our reactions. What's called a carbonyl group. Carbonyl group is a carbon with a double bonded oxygen to it. And then there's either an R group or an H group or something down here on the sides. But this is what's called a carbonyl group. Carbonyl is carbon with a double bonded oxygen to it. Okay. Now, carbonyl groups are used in different types of functional groups. We can have let me see if their list is here, okay? So we already talked about alcohols and ethers. With a carbonyl group, you can have R, C double bonded to O, bonded to H. Okay, if a carbonyl group with a hydrogen, this is called an aldehyde. And again, these are all in your book. So just have to learn how to recognize them and know what they are. You have to memorize them, but once you see it, you have to know what it is and how to write it on there. So if there's an H attached to a carbonyl group with an R, that's an aldehyde. If you have an R group, carbonyl group, and another R group, instead of a hydrogen, replace that hydrogen with an R group, this is what's called a ketone. Okay, ketones are used in measuring urine. If your body's filling ketones, you're diabetic. That's what you're measuring for ketones when you're measuring urine, a urine sample. Okay. If we take this aldehyde and instead of putting an H, you put an OH. Okay. So instead of our hydrogen there, we have an OH group. Okay. You look at it, you'd see alcohol. You have this functional group here. That's a carboxylic acid. Okay, so we've talked about alcohols, aldehydes, ketones, carboxylic acids, esters. If you have that R group with a COO, and instead of this H right here, we put another R group right there, another carbon group on there. Okay, that is an ester. Remember, ethers have the ROR. This was an ether. That is an ester with a carbonyl group. Esters have carbonyl groups. Okay, so whether it's an H or another R, so you have an aldehyde, you have a ketone, you have a carboxylic acid, you have an ester. We talk about ethers and alcohols. Okay, so those are functional groups. Now let's do, a lot of our drugs contain nitrogen. Okay, so if it's containing a nitrogen group, okay, it's going to be an amine or an amide, depending if it has a different attachment. Let me get to your, where do they have it on here? They have esters. Okay, so if you had an R with a nitrogen group, say NH2, that's an amine. We have an R with a carbonyl group bonded to a nitrogen group. That's an amide. Okay. So when nitrogen has a carbonyl group to it, that's an amide. When it just has a hydrogen on it, that's an amine. Okay. So nitrogen, when there's a nitrogen, it can be either amine, which means it's just bonded to hydrocarbon, or an amide, which means it's bonded to a carbonyl group. Amides are going to be your amino acids, which build up your DNA, your proteins from DNA molecules, which we'll talk about in a little bit here. Okay. Right, dopamine, serotonin, those are all amine groups that affect the body. Acid bases, let's see what else they have here. Okay, perfect. Let's go to, we're talking about polymers here. Polymers are just a unit that repeats itself over and over, like plastics, like Teflon, non-stick surfaces, things like that. Those are all polymers. Polymer is a group that opens up a double bond and then to repeat itself. So it gives you a unit. The unit repeating is a monomer, like polyethylene. Polyethylene is carbon, bonded to hydrogen, bonded to hydrogen, bonded to hydrogen, bonded to hydrogen. And this group links and repeats itself n number of times, 100, 1,000, 10,000. It's that one unit repeated over and over and over again. And what it is, you open up a double bond and allow it to bond between there. So we start with this monomer, which is a double bond between everything. And we open up this double bond. One electron goes here, one electron goes here, and then it can bind and form this polymer. That's all a polymer is a repeating unit of a monomer. Okay, polyvinyl chloride, PVC pipe. Okay, polyvinyl chloride is your, this is the compound here, it's C, hydrogen, hydrogen, and then I think there's one chlorine in it. Chlorine and a hydrogen. Okay, and the monomer was C, chlorine, hydrogen, hydrogen, hydrogen. And this bond opens up, allows a bond over here. One electron goes here, one electron goes here. You can form a bond at both ends. And you build this chain. As you build this chain for a monomer, that is a polymer. Like polyester, polyvinyl chloride we talked about. We use polypropylene with just a CH3 group in one of the places, but it's just a monomer with a double bond between the as your monomer. That double bond opens up to allow you to add more to it, and it links it together in over and over that same monomer unit. So the same 6 elements are linked over and over and over n amount of times, where n could be 1, 2, 3, 10, 100, 1,000, 10,000. It could be a whole series of links. That's how you make polyester. That's how you make different polymers. And one more section, and we're done with chapter 15 also. All right, biomolecules. Talk about DNA, RNA, and how they work. Different carbohydrates and sugars, all made up from a carbon background. Okay. We use glucose as the sugar in combining these for storage in our bodies. Polysaccharides are natural occurring polymers of carbohydrates. What we do when we eat carbohydrates, we break it down into simple sugars. Okay. Then we use those sugars to link together and form a long chain, which is basically a polymer of these sugars. And we link it over and over and over again to the same repeating unit, and we use that to form triglycerides, and that's stored in the body as fat. Okay. Once you want to use that, we can call on our fat reserves to break it down and produce sugar back into our bloodstream to give us energy. Okay. But we store sugar as polymers. Same as before, it just links and repeats that link over. Okay. That's our carbohydrate. Now we have basically 20 amino acids in the human body. We use those 20 amino acids to build every single protein the body needs. It's built out of these 20 amino acids. Each of those 20 amino acids has the exact same formula, except for one part. Okay, so every amino acid is going to have an NH. Let's make this neater. Oops, sorry about that. NH3 bonded to, it's going to be a plus sign over here, carbon, hydrogen, okay, and it's going to bond to carboxylic acid. Okay. Every amino acid, there's this carbonyl group here, there's carboxylic acid, carbonyl group with carboxylic acid, nitrogen, and amine group here. Okay, and then this part here is different. Every amino acid has the exact same thing except for the R group, and they have different names for it. So if that R group is a hydrogen, it's glycine, and there's a 3-code abbreviation for glycine, which is GLY. Okay, if it's a CH3 group, it's alanine, it's ALA. So if it's a hydrogen, it's glycine, it's CH3, and they can get complex. There's a whole list on table, what's in your book, 15.4. They give you the 20 amino acids, they give you the whole list of all of them. Okay. And they all have a different 3-digit code. And those 3-digit code is used to build your proteins. Okay, like if it's alanine, glycine, valine, leucine, that sequence of amino acids is what determines your protein. Okay, and that sequence of amino acid is determined by DNA. DNA, since the body opens up, it's a double helix, opens up into RNA. RNA transfers from the nucleus of the cell into the cytoplasm, and cytoplasm is read by ribosomes, which put a code attach and attach amino acids into a chain in the proper sequence. So your DNA sequence determines the RNA sequence, which determines the amino acid sequence. Okay, so DNA determines your amino acid sequence, which builds your proteins. Okay? And that's what forms your, they're called peptides or peptide bonds. And the polypeptides as a group more together. Like I said, every single one of them has this exact shape. So this bonds to another carbon group, this bonds to another nitrogen group. So put a nitrogen here, and then put an oxygen, carbon, carboxylic acid group here, and continue. And it bonds and it spreads out. Okay. And it just links these amino acids together into this chain. And it's called peptides bonds that link it together. Okay, draw the structure of. Okay, so if you see the R group here, you'll know what amino acid it is. Okay, so let's do an example here. If we had, let's say we had NH3 as a positive charge, CH, and we have a CH3 coming down here. And then we got our CO bonded to NH, bonded to CH, bonded to CO, NH, bonded to CH, bonded to COO minus. And one we have CH3, this other one we have CH2, CH, two CH3 groups, and here we have a hydrogen group. So again, this chain is always going to be this repeating unit right here. And it's going to repeat and repeat and repeat. And the only thing difference is this R group that's attached. And if you look at the amino acid group, this is alanine, which is ALA, which is CH3. The CH2, CH3, CH3 is leucine, which is LEU, and hydrogen is glycine. So that's an amino acid of alanine, leucine, and glycine. Okay. And it can be made up of hundreds of these amino acids, or thousands, or 10,000s of them. Okay. And as we talked about the DNA coding it for, DNA has 4 basic codes that attach that allow you to determine what these are. They have 4 bases called adenine, thymine, glycine, and cytosine. Adenine always pairs with thymine, glycine always pairs with cytosine when you're doing your amino acid. And that's what holds these double helix around. Think of a ladder, you kind of bend it. That's your DNA double helix. And they store all your genetic code. Okay. That's basically all I want to talk about. And I think that's the end of chapter 15. All right. That was 14 and 15. We got through all those. Any questions on 14 and 15? If not, we will start with questions from the let me get my emails up. And then we'll do the ones that were submitted here. Columns, let's see if anyone asked any from any emails so far. And let's move this over here so I can see it. Zoom, 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 zoom. Checking, that looks good, that looks good. Okay, I think I answered that one. And Stephanie had a question, but let's answer some from.
Can we answer questions from the people that are present in class?
Yeah, I'm gonna do yours right now. Yep, I was gonna get yours right now on the email. I just gotta
Thank
put
you.
my emails right here. Where'd you go? There you are.
Yeah, it's text messages.
Yep. All right, so the first one was complete and balanced molecular equation for the reaction of aqueous chromium 2 bromide. So aqueous chromium 2 bromide and aqueous sodium carbonate. Sodium plus sodium carbonate. Include the physical states. Okay, so these are both aqueous, AQ, and it's going to go to sodium bromide, NaBr, and that's going to be aqueous, AQ, plus chromium carbonate. Now, is chromium carbonate aqueous or solid? Let's go back and look at my list. chromium. I don't see chromium on here. So, all right. Shoot. There we go. Let's look up chromium carbonate real quick. And it was CrCO3. Soluble in water. And let's give it a shot for now. All right, let's reduce carbonate is insoluble in water. So chromium carbonate is a solid. That's a precipitate. If you look in your book, you'll see that's a solid. And those are the compounds. Now I got to balance it. We have 2 bromines. So I put a 2 in front of here. And 1 chromium, CO3, 1 CO3, 2 sodiums, 2 bromines. That should be balanced. So that should be it. Okay. The NaBr is aqueous, the chromium carbonate is solid. Okay. And then it says enter. So that should be the first step. Then it says write the balanced net ionic equation. Okay, net ionic equation. All right, so now we got to break it apart. We have chromium 2 plus 2 Br minuses, bromine minus, plus 2 sodiums, plus carbonate. Goes to 2 sodiums, plus 2 Br minuses, plus CrCO3 solid. That's our precipitate. So our spectator ions are sodium, bromine. Our net ionic equation is chromium 2 plus aqueous. That's an AQ. Plus CO3 2 minus carbonate ion, which is aqueous also. Goes to CrCO3 chromium carbonate, which is a solid. That's your net ionic equation. Does that make sense?
Yeah, it makes it more clear. Thank you.
Okay, no problem. Next one says, when completely filled with water, the beaker and its contents have a total mass of 351. What? Volume. Okay. A beaker. Okay, when completely filled with water, a beaker and its contents have a total mass of 351.2. Okay, so you have a beaker filled with water, and the mass of that beaker is 351.25 grams. The beaker and its contents, that's what everything weighs. What volume does the beaker hold? Density of water is 1 gram per milliliter. You gotta know the weight of the beaker. Completely, oh, empty beaker, it's right there. I didn't see it, sorry. It's above the equation. The empty beaker weighs 46.77. Okay? So if the beaker weighs 46.77 and the whole thing weighs 351.25, the total mass of water is equal to, that's a 2, 351.25 minus 46.77, right? You just subtract the weight of the beaker from the weight of the water, or the weight of the beaker dry with the weight of the beaker plus the water. So 351.25 minus 46.77 equals 304.48. So the water is 304.48 grams, And we know the mass of water is 1 gram per milliliter. Okay, so the volume of water is 304.48 milliliters. Did I answer that right? Let's see.
I answered the first part correctly. I just had trouble with when it said how much would the beaker and its contents weigh if it was completely filled with mercury. And it says
Okay.
the density of mercury is 13.5 grams per milliliters.
Okay, so you still have the mass of mercury. Oh, the mass would be a lot different. How much would the beaker and its contents weigh completely filled with mercury? So you would have same volume. So you would have 304.48 milliliters, right, of mercury. You have the same volume. And the mass would be, how much would the beaker and its contents weigh? So the mass of mercury would be 13.5 grams per milliliter. So 304.48 times 13.5. Oh, shoot, the wrong numbers. 304.48 times 13.5 equals 4.11. Well, 4,000, let's do it this way. So keep everything the same. 4110. 4110.48. That's how many grams of mercury, right? And the grams of how much does the beaker weigh? The beaker weighs 46.77, right? So this is how much mercury weighs. This is how much the beaker weighs. And it's asked for the mass of the mercury and the beaker, the total combination, right? That's what it's asking for.
Yeah, it's asking how much would the beaker weigh and its contents if it was completely filled with mercury.
Okay. So the volume would be the same. So it would be 4,000. Okay. Here's my calculator. 4,110.48 plus 46.77. Because it'd be the weight of the beaker and the weight of the mass, it would be 4,157.25 grams. That'd be the weight of the mercury plus the beaker. Because the beaker is not going to change, mass of the beaker. But the mass of the water is a lot different than the mass of the mercury, even though the volume is the same. Mercury is a lot more dense. Make sense?
I think it's asking, yeah, I think it's asking for the answer in scientific notation because when I click on it, it already has a setup.
Okay, then put 4.16, if you want 3 digits, times 10 to the, where's that decimal point? 1, 2, 3. Well, I get more decimal points than that. Okay, would that be the weight of the, that being scientific notation? Does that make sense?
Yeah.
Okay.
Thank you.
Sure. Write the balance equation for the reaction of copper with sulfur. Includes copper with sulfur. It doesn't make sense. Write the balance. I think we're missing something. Chemical equation for the reaction of copper with sulfur.
Yeah, and then it's asking to include phase symbols.
Yeah, but you have to have I mean, solids? It has to tell you what you're starting with. Was there some part of the question before this?
Yeah, and I figured it out almost, but it said I had the correct equation, but it wasn't correctly balanced. Like I'll pull it up.
We might have a charge or something on there. I don't, copper plus sulfur. Are they both solids? Is one an aqueous form? You have to know what you're starting with.
It just says select the metal and the non-metal, so the copper and sodium, I mean copper and sulfur. It gives me Cu parentheses S plus S parentheses, then it equals CuS parentheses S.
Okay.
Then I have to balance that.
Well, that is balanced. Cu.
Yeah, that's the thing. I put that so many times and it said that it wasn't balanced. So then I'm like, what am I doing wrong?
It's not written right. You have to have copper plus sulfur. Let me see something. So there's something missing. Copper sulfide. Yeah, it's not copper sulfide.
Yeah, it's asking the balanced chemical equation for the reaction of copper with sulfur.
Yeah, but is it copper 1, copper 2?
No, it doesn't specify.
It has to, because copper's a transitional metal. So copper, it could be CuS, could be CuS, Cu2S. Because it could be +1, it could be +2. It's not making, it's not giving you a complete question.
Yeah, that's what sapling is like for most of the questions.
Because sulfur can be, I mean, it can be S8, S4.
Yeah, because what I put as my answer was Cu parentheses S plus S parentheses G equals CuS parentheses S, and it says that it's correct, but it's not balanced, so it's not fully correct.
Copper sulfur gas? You put a G or an S?
For sulfur, I put a G
Why?
because it seems like they're boiling it, so I'm assuming it's a gas.
Was this from the lab?
Yeah.
Oh, there's something in the lab we're missing then. What happened before this? Because you gotta, yeah, there's something in the lab that's not here. There's something in the lab that has to, whether it's what state it's in. Are they boiled? They have liquid, they have gas, sulfur?
It just literally just shows me a picture of something being lit on fire. So
Is there a liquid anywhere?
no, there's no liquids. It's just these two things being lit on fire, and that's pretty much it.
So it's two solids been lit on fire.
Yeah.
Okay, so it'd be copper solid plus sulfur solid. It wouldn't be a gas. They're both solids. It might be because there's two solids being mixed. So it has to be copper solid plus sulfur solid. Goes to CuS. And the result's a solid, right? It's a different color.
Oh.
Different color.
Yeah, that makes sense now.
Okay. I knew there had to be something they're doing. Okay. So that should work.
Yeah, it worked.
Okay, perfect. Which one was that? That was 1, 2, 3. This is the fourth one now. Whoops. come on. One, two, three, four. All right, potassium nitrate. All right. We'll keep it up so I can see it. No, lead. Whoops, which one am I at?
Yeah, it's the potassium nitrate one.
I'm having a hard time with cell phone here. 1, 2, 3, 4.
Yeah, it's the fourth one.
Potassium nitrate has an molecular mass of 101.1 grams per mole. You write it down, 'cause I can't keep seeing on the. It's not showing it right on my cell phone. So potassium nitrate has a molecular mass of 101.1. Okay. In a constant pressure calorimeter, 12.3.
I can read it for you if you want.
Yeah, constant pressure calorimeter, 12.3 grams potassium nitrate, right? So 12.3 grams of potassium nitrate is dissolved. In 287 grams of water, 23 degrees centigrade. 287 grams of water at 23 degrees centigrade. Okay. The temperature of the resulting solution decreases to 20.8. It goes from 23 to 20.80. Okay. Assume that the resulting solution has the same specific heat of water, 4.184. Specific heat of water, 4.184 joules per gram degree centigrade. And that there is negligible heat loss to the surroundings. How much heat was released by the solution? So Q, the heat released by the solution, equals specific heat M delta T. That's your formula, right? So you know the specific heat, you assume it's going to be the specific heat of water, 4.184 joules per gram degree centigrade. The mass of the solution is 287 of water and 12.3 grams of potassium nitrate. So 287, 297, 299. Is that right? 287 plus 12.3. 287 plus 12.3. 299.3. Okay, there's your mass. And the change in temperature went from 23 to 20.8, right? All those numbers right there? I'll try to read it off the phone. So your change in temperature is 23 minus 20.8, which comes out to 2.2. That's your change in temperature. So 4.184 times 299.3 times 2.2 comes out to 2. What do we go to? 3 days is 12.3 grams. 2.75 times 10 to the 3 joules of heat. So 2.75 times 10 to the 3 joules. That would be the heat produced. Does that make sense?
Yeah.
Okay. What is the enthalpy for the reaction?
Oh, I got
Once
that
how
one
much heat
right.
is produced. Oh, okay. That makes sense though? You got
Yeah,
that right? You got the other one wrong?
I don't know if it was like I mixed up the numbers or something, but I don't.
Yeah.
Yeah,
You
but
use
for
the
the
right number, get the second.
yeah for the 2.75 times 10 to the third joules for the first one, it's actually wrong. Still.
No, it should be right.
Hmm.
Unless it's significant digits or something. Because 4.184, 299.3 grams, and a change in temperature of 2.2. Yeah. Did you use that for the calculation of the enthalpy? Because you have to use this for the second one. Let me see.
Yeah, maybe I just input it wrong because the sapling's really special.
Oh, no. See, it says kilojoules. So it should be 2.75 kilojoules. Yeah. Should be 2.75 kilojoules.
Oh yeah, that's what I put originally before I asked you for help, and it said it was wrong too. So I was like, how? I was really confused.
No, that's right. Yeah, it's got to be 2.75 because that's what you use to calculate the heat of enthalpy too. If that was wrong, the other one would be wrong. So yeah. Yeah, there's no other way to do it. Unless I hit my
Okay.
calculator wrong. Four point one eight four. Or what did they say was it? Let me see, just make sure they have the same numbers. Four point one eight four joules. 20.8, 23, 2.2, and 287, and 287 grams of water. I keep losing my cell phone here. I can't get it big enough to see on my cell phone. 20.8 is 12.3 grams, right?
Yeah, 12.3 grams of potassium nitrate.
Yeah, that's the answer I get. I don't see any other way to do it.
I'll just leave it as is then.
Yeah, I would. It's got to be the right answer. Okay, the next one is strontium chloride and sodium fluoride react to form strontium fluoride and sodium chloride. Reaction shown. Okay, so you have the reaction. Strontium chloride plus sodium fluoride goes to S-strontium fluoride plus sodium chloride. Can even balance it for you, right? What volume? They're all, no, this is a solid. The others are all aqueous. What volume of 0.69 moles 24 is required to react completely? What volume of sodium fluoride? So you want to know what volume of a 0.690 molar solution is required to completely with 543 milliliters of 0.600 molar solution. Okay. So we've got 514 moles. All right. So you got you got 543 milliliters of strontium chloride, right? Now you want moles per liter. So we're going to get that, first of all, convert that into liters. Okay. So that converts milliliters to liters. Milli means 10 to the minus 3. And now you got the molarity, which is 0.600 moles per liter. Okay, that's how many moles of strontium chloride you have to have. Now, 1 mole of strontium chloride is 2 moles of sodium fluoride. Okay. Now you know moles of sodium fluoride. It's a 0.69 molar solution. So you got 0.690 moles per liter. And if you want milliliters or liters, that'll give you the volume. Does it say, what does it say on there, milliliters or liters? Which one was it?
It wants volume to milliliters.
I want volume in milliliters?
Yeah, I mean, my bad. It's asking for the volume, and it's asking for the volume in milliliters.
Okay, then go back to milliliters. Okay. So your 10 to the minus 3 is going to cancel. That's no big deal. So we got 543. (543) times 0.6 times 2 divided by 0.690. Oh, shoot, wrong buttons. 543 times 0.6 times 2 divided by 0.69 equals 944. Right? Okay, 944 milliliters.
And yeah, and then it's asking how many moles of SRF2 are formed from this reaction.
How many moles of SS? So you want to know how many moles of that you're going to have. So just use the same form we have. We have 543 milliliters. Convert that to liters. And then 0.600 moles per liter. Now you got moles it. So you have 1 mole of strontium chloride to 1 mole of SRF2. So that'll give you moles of strontium chloride. So you just take 543. It is 543, yeah, 543. 0.43 times 10 to the negative 3 times 0.6. It's 0.326 moles of strontium fluoride. Because now we just gone from moles of strontium chloride, moles of strontium fluoride. It's a one-to-one relationship. Does that make sense?
Yeah, it does. Thank you.
Oh, no problem. Can't get this on myself. All right, lead-2 nitrate and ammonium chloride react to form lead-2 iodide. Form ammonium nitrate and okay, real similar one here. So lead nitrate, lead-2 nitrate. Okay. So the other formula. Uh-oh, what happened to my pen here? I lost power to it. All right, get another one. Back in here. Reconnect. And give it 1 minute to charge back up. Lead nitrate plus ammonium iodide goes to lead-2 iodide plus ammonium nitrate. What volume of 0.37 molar ammonium iodide is required to react with 297 milliliters of 0.340 molar lead nitrate solution? And it wants it in milliliters again, right? Yeah. Okay, so lead. Here we go. It's not writing up there for some reason. All right, so lead. Boy, why is it having such a hard time here? All right. Why am I not writing on this? We only do certain areas. Lead nitrate plus ammonium iodide goes to lead iodide solid plus ammonium nitrate. Does that look right? PbNO3 twice plus NH4. Iodine, 2 ammoniums, 2 ions, 2 NO3, 2 NO3s, 1 lead, 2 iodines, 2 NH4s. All right, there's your balance equation, right? And what volume of NH4 ammonium iodide? What volume of 0.370 molar? Okay, to react with 297 milliliters of 0.340 molarity lead nitrate. All right, is that what we got? That'll look right, Cassandra? Does that look like the right numbers?
Yeah, I checked it. Going
0.34.
back on tab.
Okay, no problem. All right, so we know the volume. So we're looking, we have lead nitrate. We know we have 297 milliliters of it. Milliliters. We go from milliliters to liters. And then we got 0.340 moles per liter. And we know we got moles of, we have 1 mole of lead nitrate per 2 moles ammonium iodide. And we know that we have 0.370 moles of ammonium nitrate per liter. And want to go back to milliliters. All right. So the -3's cancel. Milliliters to liters conversion, 0.3 molar, 2 to 1 moles of ammonia to 0.37 moles. Perfect. So let's do the math. $297 times 0.34 times 2 divided by 0.37 should equal 546 milliliters. Was there a second part to that one too?
Yeah, there is. It's asking how many moles of PbI2 are formed from this reaction.
Okay. So we'll do the same thing up to this point here. Again, it's 297 milliliters. And convert that into liters. And concentration is 0.340 moles per liter. And now we got 1 mole of the nitrate goes to 1 mole. You want how many moles of it? Is that what that's for?
Yes, it's asking for how many moles.
Okay. So let's do our calculations here. We have 297 times 10 to the negative 3, so 0.297. 297 10 to the negative 3 times 0.340. That's it. 0.101. 0.101 moles. That's what I get. Okay, one more here. A solution of chloride is slowly added to a solution of lead nitrate. All right, so solution of sodium chloride is added to a solution of lead nitrate. All right, so we have lead nitrate. And we're adding a solution of sodium chloride to that until no other precipitate occurs. So we're getting lead chloride plus sodium nitrate. Has to be a 2 here. And has to be a 2 here. And one lead, 2 NO3s, 2 NO3s, 2 sodiums, 2 sodiums, 2 chlorines, 2 chlorines. All right, so we're balanced. and the filtration is dry. When you weigh the total filtration, so this weight is going to be total weight of 16.73 grams is obtained. The solution of sodium chloride is added flow to a solution of the nitrate. Dried to be 17.3 grams. It's obtained from 200 milliliters of the original solution. You have 200 milliliters of the lead nitrate. All right, so that's what we got, right? He wants to know the molarity of a lead nitrate solution, right?
Yeah, that's correct.
Okay. So we need to convert everything to moles, and then we got 200 milliliters. We need to have 100 moles of that. And okay, sounds good. So 16.73 grams. How many grams per mole? Lead chloride is, what's lead? Periodic table. Lead is 207.2. There you are. So 207. Chlorine is 35.5. So that's 71. Is that right? 35, 70, yeah, 71. So it comes out to 278.2. And that moles of lead chloride. All right, now I got moles of lead chloride. So we go with moles of lead chloride. We have 1 mole of lead chloride to 1 mole of lead nitrate. That's going to give us how many moles of lead nitrate we have. Okay, so 16.73 divided by, get my calculator here, 16.73 divided by 278.2 equals 0.0601 moles of lead nitrate is going to be used for that. All right? So we know we have 0.0601 moles per 200 milliliters, which is 0.200 liters, right? Just converting milliliters to liters, because molarity is moles per liter. And that's equal to, go back to my calculator. So the molarity of that solution has to be 0.0601 divided by 0.0601 divided by 0.2. Comes out to 0.301 molarity. Okay, so you've calculated the number of moles. You know, there's that many moles at 200 milliliters, which is 0.2 liters. So then we come out to 0.301 molarity for the solution. Does that make sense?
Yeah, that makes sense. Thank you so much.
Oh, no problem at all. Those are all good questions, real good questions. All right, we're gonna do some questions now from Stephanie too. I believe she's the only other one that has some questions she wanted answered. Let's see if it's gonna be. Okay, these we haven't done these before, so that's good. Okay. So let's answer her. She says a 25 centigrade solution Aqueous solution is equal to concentration of generic cation A2 plus. So A2 plus equals 0.00343. And B minus equals 0.00686. Okay. What is the equal constant of SP for generic salt? So the salt is AB2 goes to A plus 2B minus. That's a B. Okay. Because it's A2 plus and B minus. So the KSP is equal to concentration of I don't want to put a G in there. Okay. Concentration of A2 plus times the concentration of B minus squared. Okay. That's your solubility product. Product of reactant, each raised to their stoichiometric equivalency for the balanced chemical equation. So A is 0.00343 times 0.00686 squared. And just do the math. And that should come out to 0.00343. Oops, get the wrong number. Times 0.00686 squared equals 1.6, what's it, 3 digits? Yeah. 1.61 times 10 to the, let's see, 1, 2, 3, 4, 5, 6, is it 7? Yeah, 7. 10 to the minus 7 should be the KSP. That's just our equilibrium constant. Okay. And consider organic cell, A3 plus, repeat to aluminum, and using those oxides Ag2 plus. Okay, this one is one of the one we're just talking about today, actually, the half reactions. It's Al3 plus. Al3 plus is reduced to elemental aluminum. And that would be plus 3 electrons. Balance everything. And magnesium is oxidized to Mg2 plus. So magnesium goes to Mg2 plus. And this is plus 2 electrons. This is your oxidation. This is your reduction. Right? Oxidation loses electrons, reduction gains electrons. It's a galvanic cell, right? The balance reaction take place. Half reaction, which one is the reduction, which is the cathode? This would be, for a battery, this would be your anode. This would be your cathode. Same thing, just different terminology with it. Okay, so the half reaction at the cathode is the first one. So what do you have to do to make these good reactions, Cassandra, remember? You have to make the number of electrons what?
The same on both sides, balance
Make them
them.
perfect. Yep, you got it. It has to be the same. You can't lose electrons. So the top one we have to multiply by 2. So the cathode reaction would be 6 electrons plus 2 Al3 plus goes to 2 aluminum. And the bottom we got multiplied by 3. So 3 magnesiums goes to 3 Mg2 plus 6 electrons. That way these are the same, and those are the two reactions. This is your reduction reaction here, and this is your oxidation reaction there. So you gotta have the same number of electrons, because it has to bounce by charge also. Okay, that would be that one question. This one. Draw the complete structural formula. I think the next question is missing something. But what it has is, I'll draw the line structure. We'll kind of go from there. That might be what they want. Okay, because they give you CH3, CH, CH3, CH, double bond, CH, CH2, C, CH3, H. That's what they give you. And it says draw the complete structural formula. I guess I just want it written out. So you would have carbon. There's your CH3 group. There's your carbon, hydrogen, CH3. There's your carbon, hydrogen, double bond, CH, CH2, CH3, H, CH3. That's your structure formula. Okay. That should do that. And then it gives you, it says check all the boxes that are amides. Remember, an amide has a carbon, double bonded oxygen, bonded to nitrogen. This is an amide functional group. It has to have a carbonyl group bonded to a nitrogen. So if you look on the one she has, there's only one form that has that. And that is, this is the one you would check if you're looking for an amide. Okay, and here's a group that doesn't. That's an amide right there. So that's what you would circle. And last one, nuclear reaction by supplying the different nucleus. We haven't done those yet, but I can do this for you so you can get a good view of it here. A little advance of chapter 16, because you will have something like this on your final. So it says 249.98 CF plus X is going to do a decay of 260, 105 dB plus 4 neutrons. Okay. With balancing, radioactive problems are very simple. The top numbers have to be supplied. So in other words, you have 249 plus some number equals 260. Okay. Plus 4. Get each one neutron, you have 4 of those. Okay, so you just have to balance your protons and neutrons, basically. So 264 minus 249, let's make sure we get this number right. 260. 260. Oh, plus 4. Okay, so 264 minus 249. Just the top numbers all have to equal each other. This has to be 15. Okay. And the bottom numbers have to equal each other. So 98 plus what equals, because this is 0 here. That's just a neutron, so no protons. 98 plus 6 is 105. No, 7. Sorry. I can't add tonight. It's been a long night. 98 plus 7 is 105. Just got to make these numbers all equal, tops and bottoms. And there's 4 of those number ones, that's all. So number 7 is, look on the periodic table. And what's number 7? Number 7 is nitrogen. So the missing element is nitrogen with 15 and 7. That's what's missing right there from that radioactive decay. So radiation is real simple. Just you add the tops, make them equal, add the bottoms, make them equal.